topic for today is simulation accuracy and speed. Glenn's going to be staying on here to help answer questions, so please do be as involved as possible. Use that questions panel over on the right, use that chat. Let us know if there's anything that we can answer as we go through, or even just what you're thinking. We hope that you're going to learn something new today, and so nice to get that feedback. What we're going to be going through today is a continuation of a session that I presented a couple of months ago at our virtual Design to Manufacture conference. I presented a session on extreme deformation and things that we can do to deal with those cases. I hope you're able to join for that. For those of you that weren't able to join, we will go through a bunch of the same content here, get you caught up. So I'll talk about what we mean by extreme deformation. We'll do some review of simulation theory related to that. And then we'll talk about and look at some techniques for how we can deal with these extreme cases. And then we're going to continue a bit further. Today's webinar is about speed and accuracy. And so we'll talk about how that relates to extreme deformation cases and hard problems in general. And when we start talking about accuracy and speed, we do need to introduce software. That previous presentation was pretty quick. We only had 20 minutes. We had to fire through real fast, and we weren't able to get into much detail. So I'm hoping today we can do a little more exploration of those details. We'll talk a bit about the options that you have for tackling these problems, what those software tools look like, and then hardware as well. If we want to solve fast, we need to use fast hardware, and we'll talk about how we can configure that, the things you need to look out for, and give you some tips there. So let me turn off my webcam here and we'll get into the bulk of the content. We're talking about extreme deformation. We really are talking about that difference. On one hand, we have what we typically refer to as small displacement problems. And this is where you've got some model, you're applying some loading, you're developing stresses and strains, but there really isn't any shape change. The shape that you have once you've loaded up the part is basically the same as the shape that you started with. In contrast, in large displacement analysis, we're actually going to see some change in shape. Material's going to flex, it's going to bend, and your stresses and strains are going to be larger. And when we go beyond that, that's what we're referring to when we talk about extreme deformation. These are cases where the material is really changing shape, and we're going to have really high strains. You can see in this forming example on the right, the material is almost flowing. And we care about this because it influences the type of simulation or the techniques that we're going to have to use to solve the problem. For those small displacement problems, we can use a linear solution. And luckily, that's the vast majority of things that we need to solve as engineers. And based on the poll, that's what most of you are doing most of the time, and that's great. It tends to work really well. It's really easy to do. But when we get to these harder problems, then we do need to switch to a nonlinear solution. And in those extreme cases, then we need to start looking at using specialized techniques that we're going to talk about in a little bit here. Now, there are a few different reasons that your problem might be nonlinear and you need to use a nonlinear simulation. The first is you may have a nonlinear material. This could simply be that you've taken a typical linear engineering material and pushed it past its yield strength. Or maybe you're using something inherently nonlinear, like a hyperelastic rubber, nitinol, maybe something more exotic, like a foam or composite. Or maybe you've taken a material and you've pushed it so far that it's starting to crack and fail. Another source of nonlinearity is contact. If the contact region changes during your analysis, that is going to need a nonlinear solution. And of course, we have geometric nonlinearity. So this is when we have these large or extreme deformations. Maybe we've got something that's rotating. Maybe we're trying to change how the load is applied or some other condition throughout the process of the simulation. Really, anything that's going to change the geometric stiffness of the model. Now, it's important to consider the material nonlinearity, the contact nonlinearity, and the geometric nonlinearity because all of these feed into the math that's being solved in our simulation. In a static analysis, the equation we're solving is force equals stiffness times displacement. And it's that stiffness matrix that this really all focuses on. If it's constant, like in a small displacement analysis with linear material, then we can use our linear simulation approach. But if the stiffness matrix changes, we're using a nonlinear material, or we've got large deformations, then we are going to need to use a nonlinear simulation in order to solve that. And the reason that a nonlinear simulation is needed, the reason it works, is because it can account for the changes in the stiffness matrix. And we do that by using time increments. You'll notice that time is in quotation marks. And that's because if we are taking on a static problem, there really shouldn't be any time, right? Everything should be happening slowly or constantly. And so time increments in this case really refers to a way for us to increment the load. Sometimes we call this pseudo time. And it's important to note that we're still using increments. They just don't correspond to real lifetime. In contrast, if we are doing a dynamic analysis, then of course these time increments are real time increments. Now, a little bit of review on how this time incrementation works. If we have some problem, we start at time 0 at the beginning, and we want to get to the end. In a linear analysis, we simply apply the entire load. But in a nonlinear analysis, we apply part of the load. And then we apply more, and then more of the load and more until we get to that final result. So we're stepping along the way, adding these time steps to get us to our final result. And the key here is that at every single time increment, we are going to be recalculating that stiffness matrix. We're also going to be doing iterations at every time increment. At every time step, we need to make sure that our force equals stiffness times displacement equation is balanced. This is important to make sure that we have an accurate result. Sometimes we can use bigger time steps. Sometimes we have to use smaller ones. And it's this equilibrium iteration process that allows us to determine what the appropriate time step size is. This is also where we run into a challenge when we're dealing with these extreme deformation problems. Equilibrium can be really hard to achieve for these extreme cases. And so we may need to use a lot of iterations and use really small time increments. And this can mean that our problem will take a really, really long time to solve or not be able to solve at all. So how do we deal with this? The first technique that I'd like to share is using a dynamic analysis approach to solve our static problem. The equation that we're solving is force equals stiffness times displacement. And we've just talked about how that can be hard to balance for extreme cases. It would be really nice if we could just add a term to one side of the equation to make it balance. And in a dynamic analysis, there are additional terms. There's a velocity term and an acceleration term. And these can help to make that equation a balanced one. However, if we're solving a static problem, we shouldn't really have any velocity or acceleration. What we're doing here when we take a dynamic analysis approach and use it to solve a static problem is we're not solving a true static problem anymore. But if we can keep those inertial forces small, velocity, acceleration, maybe only 1 or 2% of the equation, then they probably won't impact our final result too much, and we have what we call a quasi-static solution. We're using these extra terms to help balance the equations so that we can either solve the problem if it wasn't solving before, or maybe we can solve it a little more quickly with larger time steps. And while we aren't keeping those two inertial terms truly zero like they would be in a pure static analysis, if we're keeping them small enough, we'll still have a good result that can give us good information, allow us to make good decisions. Now, back to the time increments, we discussed how we go through, we increment, and we iterate. And this process is what's known as implicit analysis. We do also have something called explicit analysis. And the difference here is that in implicit analysis, we do those equilibrium iterations to make sure that we have an accurate converged result. In explicit analysis, there are no equilibrium iterations. And so by removing that, we get rid of the force balance problem. We no longer have to balance that equation. Instead, we make sure that we have an accurate result by using really small time steps. So in explicit analysis, there are no equilibrium iterations, and instead we're using very, very small time steps, but we can solve those time steps really, really quickly. And this makes explicit analysis really good for high-speed dynamic events. It's also really useful for these quasi-static problems that are highly unstable. Beyond that, it gets us access to the next two techniques that we're going to talk about. We're going to shift away from talking about how we solve the simulation, and I want to talk about how we set it up and how we define the mesh. I'm going to introduce two terms here, Lagrangian and Eulerian. Lagrangian mesh is the mesh that we're used to. Typical mesh where you apply it to your model. When you go and load your model and deform your model, you're deforming the mesh. An Eulerian mesh is very different. Here, we define a mesh that's filled with the material, and then when we go and deform that part, we're simply moving the material through the mesh. You can see the grid that we start with is exactly the same as the grid that we finish with. We've just changed which mesh cells have material inside them. If we look at something a little more practical, a little more real, we've got this copper rod impact, and you can see that as it squishes, the mesh is deformed. In the Eulerian case, the mesh doesn't move at all. The material is simply flowing through the mesh. The reason we use a Lagrangian mesh most of the time is it's really easy to work with. We can track the free surfaces, we can go and click on the mesh faces to apply our boundary conditions. It's only really in these extreme deformation cases where we have a problem because the mesh elements become too distorted. The Eulerian mesh gets rid of that problem. The mesh isn't moving, so there is no mesh distortion at all. But it's really hard to work with. I can't really apply boundary conditions to the surfaces. It's hard to tell where those surfaces are exactly. And a pure Eulerian mesh, a pure Eulerian analysis all by itself really doesn't work very well and isn't very practical. And so what we need to do is we need to take that Eulerian and we need to combine it with the Lagrangian approach. And there's two different ways I want to talk about on how you could do this. The first is called ALE, adaptive meshing. ALE stands for arbitrary Lagrangian Eulerian. And what we're doing here is we're going to take the Lagrangian approach, we're going to take the Eulerian approach, and we're going to mix them together on our part. We are going to attach the mesh motion to the mesh deformation, but only on the exterior surfaces. Because we're meshing those exterior surfaces, it's going to be easy to figure out where they are, and we'll be able to place our boundary conditions on them. But on the inside of the part, we are going to allow the mesh to adjust itself. You can see in that middle image, we're starting with square elements, and in the end, we're ending up with rectangular elements. So they are deforming, but they aren't deforming nearly as much as in the Lagrangian case on the left. We're allowing the nodes and elements to adjust themselves and prevent getting extreme deformations and extreme distortions, which should help to improve our accuracy. If we take a look at our pipe impact, we've got the Lagrangian example, we've got the Eulerian example, and we've got ALE in the middle. You can see that the mesh is distorting a little bit. Those elements are changing shape and size, but nowhere near the same amount of distortion as we have on the left. Okay, so that's ALE, adaptive meshing, something in between the two approaches. The other technique is called CEL, coupled Eulerian Lagrangian. Here, we are not going to try to combine the two techniques on one part. Instead, we're going to have some pure Eulerian mesh parts, and we're going to have some pure Lagrangian mesh parts, and then we're going to let those interact with each other. We're going to use the Eulerian option for the parts that are undergoing a lot of deformation, and then for the parts that aren't deforming so much, we'll use our regular Lagrangian mesh. We'll have those interact with each other with contact, and so we won't have to try to apply our boundary conditions to the Eulerian part. We'll simply apply that to our Lagrangian part. This CEL technique is really useful for these extreme deformation cases where we've got solids that are changing shape, but it also gets used a lot for fluid structure interaction problems, as we can take the Eulerian mesh and use that to represent gases or liquids too. We'll explore this CEL technique a little bit further by looking at this rivet forming example. We've got a rivet blank, and we're going to be taking the top and bottom dies and moving those in to compress and squish that around the plate in the center. If we were to tackle this with a pure Lagrangian mesh, this is what the mesh on the rivet blank would look like. And then we'd have our mesh on the plate and dies. In the CEL approach, this is what the mesh on the rivet blank would look like. Got a solid grid of mesh elements, and we're simply defining which elements have rivet material to start with. That's a cross section, and in 3D, it just looks like this rectangular block. It is important to note that it's quite a bit larger than the rivet blank. We need to make sure that we have Eulerian mesh elements anywhere that the rivet material might deform to. The mesh on the other parts, same Lagrangian mesh, no change there. Now when we run this analysis, the results are going to look very similar, but if we dive in a little bit deeper and take a closer look, we will notice some differences. In the CEL analysis, the high strain region is near the corner where we'd expect it to be. In the Lagrangian example, though, we don't get our high strains where we want them to be or where we expect them to be. Instead, we're actually getting them where we have the most mesh distortion. The mesh is getting caught up on the sharp corner, and we're getting some results that maybe aren't so accurate. And so by switching to CEL, we're able to improve the accuracy here. And a great way to see this is to take a look at the reaction forces on the top and bottom dies. At the start of the analysis, when the deformations aren't so extreme, before we have a lot of distortion and before things get stuck on that sharp corner, they actually match up really, really well. It's only later on in the analysis that the Lagrangian approach gets a little bit noisy and we can see that the CEL is a bit more accurate. Now, all this accuracy does come with a price. The CEL run here took about 5 times as long as the Lagrangian approach. And that's really where we want to go here and talk a little bit further, is that trade-off between accuracy and speed. Almost every choice that we make in simulation, all these techniques that we've just discussed, lie somewhere on this graph. We can make a choice, and that might make our analysis more or less accurate, and that same choice might make it take longer to solve, or it might make it run faster. If we recap some of the things we've just discussed, we can see what those do to our simulation. A nonlinear simulation is typically going to be more accurate than a linear simulation if we've got a lot of deformation, but it is going to take longer to solve. If we have a problem that's getting hung up on equilibrium iterations, we can't balance the equation, we might be served well by switching to a dynamic or quasi-static approach. That'll help us solve a little bit more quickly, but we're adding in those dynamic terms. So we might be giving up 1, 2, 5% accuracy if those terms are getting large. If we use our advanced meshing techniques like ALE, that can help improve accuracy, but it takes time to figure out how to adjust that mesh. And as we just saw with CEL, we get a more accurate result, but again, it takes longer to solve. Even if we take a step back away from these extreme deformation problems, even the most basic linear static problems, we deal with choices like this. If we take our mesh size, we make our mesh finer, that's usually going to give us a better result, but take longer to calculate. And if we make it coarser, we're going to end up with something that solves faster, but is probably less accurate. Every choice that we make in simulation is usually going to land us in these 2 quadrants. We're going to be more accurate and have to spend more time, or we're going to be less accurate and get our answers more quickly. And so balancing this is all about trying to figure out where you want to be. And for most of us as engineers, I'd expect that we probably want to be accurate enough, but as fast as possible. And so I have some tips here for how you can pinpoint that spot and locate yourself there. And the first is, before you even jump into this graph, before you even start thinking about your simulation, do remember that solve time isn't the only thing you want to consider. You want to consider your setup time as well. If I can spend 10 minutes tweaking my simulation to reduce the solve time, that might be good. If that 10 minutes reduces the solve time by half an hour, that's excellent. But if it only reduces the solve time by 1 minute, probably not worth me spending that time, unless I am going to run that simulation over and over and over again as I iterate my design. The other thing you have to consider here too is when you're running it. There are certainly times where I know I could have spent 10 minutes and improved my simulation and made it run faster. Maybe instead of solving in 2 hours, it would have solved in 1. But it was the end of the day, and I was going to run it overnight anyways, and I wasn't going to look at it until I got back in the morning. Who cares? It's going to solve either way. I don't need to make that change. Now, if we are jumping into this graph and we do want to focus on reducing that solve time, one of the best things you can do is make sure that you simplify your problem. And it's important to be really intelligent about how you do this. Some simplifications can affect your accuracy. When you're removing details from a model, you might be omitting things and changing your result. However, some simplifications allow you to reduce your solve time without changing the accuracy. And that's pretty much as close as you can get to that top left quadrant where we wish we could be, where we get more accurate results and faster solve times. A great example of this line heading to the left here is using symmetry in your model. If you've got a symmetrical part, you've got a symmetrical loading situation, you can go and cut that model in half. It'll solve way faster. And as long as your real life condition is symmetrical, you haven't given up any accuracy. So you want to look for simplifications like that anywhere you can, because that's a cost-free way to get answers more quickly. Now, when you get into your simulation, you do need to make sure you choose an appropriate technique. We've covered a few of the techniques that you need for extreme deformation here. And then once you've chosen your technique, you need to pick the right software to use that technique. If you choose the wrong technique or the wrong software, that can land you in the bottom right quadrant, where you're taking longer than you need to solve and getting an answer that's not so good. And so simply by choosing the right simulation technique and the right software, you can move yourself out of that bottom right quadrant, and that'll feel a lot like you're moving into the top left quadrant, which is pretty good. So we've talked a lot about the techniques, we've talked about how we can balance this, and we're ending off here with choosing the right software. Okay, what are those softwares? Let's talk a little bit about that. Got 3 different pieces of software. Oh,
We're
yep.
at a break point here, but a really good question came in, and I think it's an important clarification. What's the fundamental difference between something being nonlinear and dynamic?
Awesome. Okay, yeah. So nonlinear and dynamic aren't necessarily opposites. Something can be linear and dynamic, and it can also be, or it could be nonlinear and dynamic. I think we've done a good job covering here the difference between linear and nonlinear. Dynamic is really about whether things are moving or not. If everything is being applied, all your loads are being applied slowly with no dynamic forces, you're not making an impact, nothing's shaking, then we can probably consider that as a static problem. However, if you've got things with velocity or acceleration, then we are looking at a dynamic problem. We have blurred the lines a little bit here when we talked about using dynamic techniques to solve static problems. And so it really comes down to how fast are things happening and how much of an impact do those dynamic forces make. Hopefully that answers the question. If not, please ask again, and I'll take a second shot at answering that. But I can see that a few questions have come in. That is awesome. I see Glenn's been able to answer most of them through text, so please keep those coming, guys.
Yep. And if you haven't seen those, they're in the question section of GoToWebinar, and you can drag that out into its own window for easier reading. Leave you to it, Terrence.
Awesome. And thanks for jumping in with that, Glenn. So back to software. There are 3 different software tools I'd like to talk about here. The first is Solidworks Simulation. This is the simulation tool that's built into SolidWorks, and it's something that we're really big fans of here at Hawkridge. Because it's fully integrated, all the buttons are really familiar, all the things you do in SolidWorks are really familiar, and it's really easy to use. It's also really easy to go back and forth between your CAD modeling and simulation, and this really efficient workflow allows us to get good insight into our designs, where we can iterate quickly and make good design decisions. Now, there are 3 different packages of SolidWorks Simulation: SolidWorks Simulation Standard, Professional, and Premium. And depending on which package you have access to, you'll have access to different types of studies. In the standard package, we can handle our static analyses. And then as we move to the right, we can take on more types of analysis like frequency, buckling, all the way up to nonlinear and dynamic studies in Simulation Premium. And so SolidWorks Simulation has a really good range of capabilities. We can tackle most of the problems that we need to here: small displacement, large displacement, but there is a limit to how far we can take this. When we get into extreme deformations and we start looking to use specialty techniques like explicit solving, CEL, ALE, these aren't available in Solidworks Simulation. And so we need to consider switching software tools at this point to something like Somalia Abacus. Somalia Abacus is a tool that's been Somalia Abacus is a tool that has been around for a really, really long time. If you're not familiar with it, it is something that historically we've referred to as an analyst level tool. It was something that a real specialist would use, somebody that does a lot of analysis. Maybe that's the main part of their job. Maybe they did extra schooling on finite element analysis. But over the past 5 to 10 years, we've really seen a shift here, and we're seeing a lot more regular everyday engineers start to use these tools. A bunch of different reasons for this. One of them is that the tools are getting a lot more user-friendly. They're easier to use, the buttons are where you'd expect them to be. They're also getting way better integrated with our CAD tools. So rather than having to hop into a clunky simulation modeler, we can simply take our models from SOLIDWORKS, bring them in, and we can do that associatively. So while we're not working in SOLIDWORKS anymore, we can go back and forth and do those quick iterations and get that good design insight. And it's awesome that more people are using these tools because it means more people are able to access these really powerful solvers and all of these powerful options where you can tackle these extreme deformation problems, contact problems, complex material behavior, or even multiphysics. The last simulation tool I want to bring up is 3D Experience Somalia. This is essentially Abacus on the cloud. The user interface is different, but it uses the exact same Abacus solvers. So you get the exact same capabilities as you do with the traditional Abacus tool. The big difference here is it is on the 3D Experience platform, which is a cloud-based platform. So you're going to be accessing this through going to the platform through your browser, accessing over the internet, and your data is going to be stored on the cloud. And I think we all know there's lots of advantages to using cloud tools in this day and age. Now, for all 3 of these tools, I want to talk a little bit more about them and how you might want to configure them. But before that, I think we need to introduce and talk a little bit about some hardware items. Obviously, if you can use fast hardware, that can help you solve things more quickly. I'm going to do a quick plug here for our Hawkridge Systems hardware guides. Every year, our support team writes 2 guides, a recommended hardware guide and a comprehensive hardware guide. The recommended guide goes through OEM solutions. So if you want to buy a computer from Lenovo or HP, we've got some recommendations on what you might want to choose. And then the comprehensive hardware guide goes through all the bits and pieces, processor, memory, graphics card, and what you might want to consider. These are available on our website, and I've also dropped them in the handout section of the webinar. So you can pull those down and download and have a read through those. Both of these guides are written for SolidWorks in general. But if you go to the upgrade section of each, you'll see recommendations for people that are using a lot of simulation. And they're going to focus on the individual components, which are the processor, CPU, graphics card, GPU, memory, and your hard drive. The memory and hard drive, some easy recommendations here. Make sure you get lots of RAM, 32 gigabytes, 64 or more. And for your hard drive, get a solid state drive. These are easy recommendations because memory, hard drives are relatively cheap. You do not want these 2 items to be your bottleneck. What probably will be your bottleneck is your CPU. We need to discuss that a bit further. And while GPU is very important when you're setting up your model, rotating things around, with one exception, GPU isn't going to be relevant for our simulation calculations. Now, when we talk about CPU, there are two main things, two main specifications that you'll see. The first is clock speed, right? 3, 4, 5 gigahertz. And the other is the number of cores. Most high performance machines are now 6, 8 cores or more. As you increase the number of cores, you can typically solve faster. And if you go way beyond what you'd normally put into one computer, you start connecting computers together, we get into the realm of high performance computing, where people will create clusters of computers to solve together. The thing that's really important to be aware of when we start talking about increasing number of cores or getting into high performance computing is the scalability of the software and the problem. Some problems and some softwares have really good scalability, where if we go from 4 cores to 8 cores, we cut the solve time in half. If we go from 8 to 16, we cut it in half again. However, sometimes we have poor scalability, where when we go from 4 cores to 8 cores, our solve time doesn't come down very much. Maybe we're solving in 60 minutes and now we're solving in 55. There are even cases where the scalability is so poor that the additional overhead to split up the problem makes the solve time longer, where it goes from 60 minutes to 65 by breaking it up further. And so that's probably the most important consideration when you think about adding more cores is it going to be worth it? Now, if you want to get really into the weeds and compare individual processors, I can't make a recommendation here. All I can do is say that you'll have to look at some benchmarks. There's a lot of different resources out there that compare different processors, how fast they can run for different types of calculations or problems, whether you're trying to play a video game or solve a simulation. One website or one company that I found that can be quite useful for us as SolidWorks users is Puget Systems. They're useful because they run specific benchmarks for SolidWorks tasks. So you can look at how those processors perform specifically for SolidWorks. For most of us, though, I don't think we need to get into the benchmarks. I don't think we need to look at individual processors. Depending on which software you're using, I have a few guidelines here, and if you follow those, you'll be able to get really good performance without having to spend all of your time researching computer hardware. For SolidWorks Simulation, the guideline is pretty simple. It's choose a faster clock speed over quantity of cores. So if you're looking for a new computer, you're looking at the spec sheets, you're comparing them. Usually the one with a faster clock speed is going to give you better performance. Now, I am assuming that you're purchasing a new computer today. The reason I say that is most computers today come with 6 or 8 cores at a minimum if you're buying a workstation. SolidWorks Simulation does take advantage of multiple cores, but it's around that 6 or 8 core mark that we start to see diminishing returns. SolidWorks Simulation has limited scalability once you get past that. You will see slight improvements all the way up to 16 cores, but it's not enough to overcompensate for a slower clock speed. And so you really do want to focus on that. The more calculations you can do per second, the sooner you'll get your result. And mentioned earlier, GPU isn't really a concern. There is no GPU solving capability here. So when you're buying your graphics card, it's really just to help with designing your models, building your assemblies, rotating things around. All of your solving here is going to be on the CPU. Now the recommendations for Abacus are a little different. The clock speed is still important, of course. The faster you can solve those calculations, the faster you'll get your answer. The difference here is Abacus, for large problems, has very, very good scalability. So we can scale past 8 cores up to 16, 32, and we can start building clusters of computers for high performance computing, and it'll still scale well. So unlike SolidWorks, where we had a limitation on how much hardware we can use, we don't really have that here. We can keep increasing the number of cores, and we can keep solving faster and faster. What we're going to run into as a limitation here is a limitation on cost. Right? If we're trying to solve faster, we can spend more money and keep going, but do you really want to spend all of your money on buying 5 computers or a ton of processors? And the licensing cost actually goes up with the number of cores you're using as well. The good news is, if you have a problem that is expensive enough and worth enough to solve really fast, you can do that. Last note here is this is the one exception to that GPU rule, is Abacus standard can take advantage of a graphics card. One benchmark that I've got pulled up here, you can see that comparing running on 8 cores versus running on the same 8 cores plus one graphics card, we get a huge speed up, right? Way faster solving just by adding that one card that was already in the machine. And so when it is possible to use this, it is really useful. The challenge here is you do have to make sure that you're using compatible graphics card that supports this type of thing. This benchmark that I got on screen here was pulled out of a white paper from NVIDIA, and I am posting that white paper to the handout section right now, so you can go and grab that from the webinar. Now for the third simulation tool, the Somalia tools on the 3D Experience platform, we talked about how this uses the same Abacus solvers. And so it has the same good scalability as Abacus. The difference here is it's on a cloud-based platform. And so we can solve faster by using more cores. And in Abacus, we had to spend more money in order to solve even faster. Here, we can solve simulations on the cloud. And so we can push our solve times down without having to spend a bunch of money on hardware. All right, this is probably the biggest advantage of the cloud, is that we can use somebody else's computers to do our work. This keeps our machines free so we can do other things with them, and it really allows us to get around that limitation. So now that we've gone through the software and the hardware, we can add one more item to our list. If we've considered our setup time and our solve time, we've simplified our problem, we've picked the right technique, we've picked the right software, the last thing we can do is throw more hardware at the problem. So either get yourself some really nice hardware or solve on the cloud. And with that, that brings us to the end of the presentation. Sorry, Glenn, I can hear you a little bit there.
It's an interesting point there to finish, right? And how would you weigh the importance of like making smart decisions in the software versus getting better hardware? What's more likely to have an impact?
In my opinion, I think that you are way better served up near the top of this list than down at the bottom. As much as I love to talk about using fast hardware, and I think cloud solving is great, you're going to see the biggest gains by making intelligent choices in how you set up your simulations.
Absolutely, and that is, I think, borne out even more so if the software doesn't scale well on multiple cores, if it's fairly linear in its process, right?
Absolutely, yeah. You're definitely going to get the biggest gains from making good choices and being able to simplify the problem, make the setup something that can be solved better or more easily, more accurately. That being said, there have been times where I've been lazy or maybe I didn't know the best way to do something. And it can be nice to throw a huge piece of hardware, throw 100 cores on the cloud to solve my problem overnight when I really should have made better choices. That's the luxury that we have now with the cloud.
Thanks, Terence.
Not sure if there are any other questions that came in, Glenn, that we need to address.
There are lots. What about scalability of a CFD tool like SolidWorks Flow Simulation? How do you describe that?
Yeah, so SolidWorks Flow Simulation does scale quite well. It is subject to diminishing returns at some point, though. I think the last time we ran some benchmarks, it was around the 16 core mark that we really stopped seeing big gains.
Awesome.
Yeah, of course, dependent on the specific job.
And then one last one. Great question from Juan. He's asking how substantial the difference would be to use a simplification like beams or shells.
Great question. And yes, those are typically great things to use. Just like using symmetry, if used appropriately, these have minimal impact on any sort of accuracy and can offer huge speed up. So definitely, if you have thin geometry or you have long, slender geometry, switching to a shell or beam mesh is a great choice.
Absolutely. And then a softball, Umesh has asked if there'd be a recording of this webinar. And the answer to that is absolutely. It will be posted both to you in a direct email once we're finished, and it will be hosted on our blog and YouTube. So thank you for that question, Umesh.
Excellent.
And I think that's it for now, Terence.
Awesome. Well, yeah, thank you very much, everyone, for attending today. Really appreciate your time, and I hope you found this useful. If you do have any follow-up questions afterwards or want to know more, feel free to get in touch with us. We'd be happy to discuss any of the content in here or anything related in more detail.
Absolutely. And we'll continue to stay here and answer questions as they come in over the next few minutes. But as you leave, we've asked a question in the follow-up survey that asks, what the last major analysis challenge you faced was? And if you want to share some context and some information, we'll share a tip or trick that might help you out. So look for that question and share some information, and hopefully we can help you out a little bit there. Okay, well, it doesn't look like we're getting too many more questions. I think we've answered most of them, and if we have missed one, we will get back to you individually. But otherwise, we really appreciate you joining us today, and we hope to see you at a future conversation or a session like this in the future. So thank you all.
All right. Thanks, everybody, and thank you, Glenn. I'll go ahead and stop the session now.